choices for me around the origin for x, so I can see the behavior of the function on this side. And since it's going to be 1/2, what is 1/2 raised to the negative 2? 2. Well, you're going to flip this over. This will be 2 raised to the positive 2. Uh-oh, move my graph. Or 4. Okay. 1/2 raised to the negative 1 will be 2. 1/2 to the 0 will be 1 again. And 1 will be 1/2 and then 1/4. And you can see the same exact behavior that was happening the other way is now going this way. At -2, I have 1, 2, 3, 4. At -1, I have 2. At 0, I still have 1. At 1, I have 1/2. And at 2, I have 1/4. And you see it's doing the exact same behavior in the other direction. So numbers between 0 and 1 for our a value, the base, is going to be considered exponential decay. Remember, we like to read everything from left to right like a book, right? So as we read from a book, this thing is dropping, it's decaying, and this thing is growing. Okay, and it's all determined by the value of a in front. Okay. One thing that's worth noting is that for all of these, f of 0 always equals to what? 1, because anything raised to the 0 power is 1. And this is actually a good thing to think about, because if we're looking at it from this perspective here, where we have both growth and decay, when, say, perhaps we could call this axis, instead of x, we could call it t for time. At time 0, how much of something is there? 1, which would be a good unit place to start, wouldn't it? So we can either decay from there or grow from there. Of course, you have to understand that if you want to talk about, although my bank account pretty much is reflected by the decay amount here, but if hopefully you could find a bank account that was going to be on the grow side, what you would do is you don't usually walk into the bank and say, here's $1 I want to put in my investment. You put in some initial amount, right? So if we look at these functions, like if you have some initial amount, a sub 0, times your function like this, then this number right here, because a to the 0 will always be 1, 1 times your initial amount will always give you your initial amount to start with. For example, 2 times 3 to the x would take this whole 3 to the x that we already have here, or I think that was 3 to the x. Yeah, 1, 2, 3, right. And move this thing, well, we would do what? We'd start at 2 and go up, because 2 would be the initial value. Now let me use the software here to show you some of this stuff without my terrible handwriting. You'll see what I mean. The first one on here is 2 times 3 to the x. Not the best thing I've done here, but h is now my function 2 times 3 to the x. And that's what's the first one on your worksheet, right? And we're going to try and estimate what it looks like on a piece of graph paper. Well, you know when x equals to 0, what's the value of 3 to the 0? 1. 3, remember, exponents become 4 multiplication. Think PEMDAS. Parentheses, exponents, then multiplication. So you put in 0, it'll be 3 to the 0, which is 1. 1 times 2? All right, so the initial value has to be a 2 here at x equals to 0. Now, is this number, don't look at the 2, but the number here, is that bigger than 1? It is, so are we talking growth or decay? Growth, so this thing is going to ramp up this way pretty quickly. That means on the other side over here, it's going to decay, if you will, that way. Now the 2 has a slight effect of multiplying everything by 2. In the long run, if you think about it this way, if you're taking 3 and raise it to a power, 3 squared is 9, 3 to the third is 27, and then you times that end result by 2, by the time you get up into the x's like 100, 3 to the 100 is so big that multiplying it by 2 is actually insignificant, right? I mean, it is significant, it's doubling it, but each time you go out in the x, that extra exponent is going to ramp that thing up so much faster than that first number that eventually it really stops making any difference what this initial value is. And you'll see this in the graph. So what I'm going to do now is I'm actually going to graph, the graph will move so mine won't match up. I call that the H1, so that's going to be C. Let me do this here. Yeah. See, the graph moves so mine didn't match up. But when mine was down here, notice that it does indeed go through the 2 that we said it should, and that it has the decay on this side and it's growing exponentially here. So on the worksheet that I gave you for number 1, I want you guys to roughly kind of draw out some of the important aspects here. Important aspects being the initial value of 2, the fact that it's growing. I want you to make an asymptote on this side because that's important that you understand that it rides down towards 0 as we head off to negative infinity. And then some of the key points that you want to hit usually refer to like -1 here and 1 here. To give you an idea of what's happening on either side of the origin. So when you put that into, remember our function is 2, 3 to the x. When x equals to 1, what is this value equal to? Alright, so here's 6. Notice that lines up with the 1, that lines up with the 6. Which means that when this x is equal to -1, what do you have? You have 2/3, right? You see that? -1 will make this 3 go down and be +1. 2 times 1/3 is 2/3. So that looks to be roughly, if this is 1 right here, then this is 2/3. So you can get some key points by using 1s. Why use 1s in these exponents? Because they're pretty easy to work with, right? Something raised to the first power is not hard to do. You don't always want to use points like 3 and 4. That could be a little more difficult. Although 2 is not bad here either. At 2, what is 3 squared? 9 times 2. So at 2, I should be all the way, well, I am. If you line 2 up, if I'm doing a good job, I can't even get 18 is going to be way up there, right? I can't even get there on this yellow graph yet. On this side over here, what about -2? That's going to be 2/9, or 2/9. So that value right there must be roughly 2/9. And it looks like it's 2/9, doesn't it? And as you continue out, this is going to get smaller and smaller and smaller and smaller. Well, this is going to get bigger and bigger and bigger. So I'm only after rough drawings on this thing for you guys to get familiar with how exponential functions look and behave. Not trying to be precise. I don't need you to be exact. I just want you to pick some key points. Again, let me reiterate. Key points are always the initial value. Some other key points would be what's happening where x equals to 1. See if you can find those, because those are generally easy to find. Other than that, just use your common sense on what the function might go for. I'm not going to, well, obviously, I'm not grading it. It's for your own benefit, and you can see the answers are on the very last page. Well, actually, sorry. Yeah, on the second page.
You're not going to have to write these out on the test. It'll be like multiple choice, right?
That's probably the thing, although I'm not ruling out the possibility of actually giving you a test where you have to draw one of these. I'm not ruling that out yet, but more than likely you'll be picking them from a list. Reason being is it's easier for us all to agree that one is doing something instead of me having to decipher 30 different versions of what it looks like. But when it comes to these, I may still have you draw one on a test. Not out of the ground yet. All right. Let's take a look at, I think you guys can handle the next one. Let's go down to number 3 because I want you to see what happens when you get exponential decay here and how I know it's decay. We have y is equal to 4 times 1/2 to the x power. How can I say for sure that this is decay?
Does that half sign?
Because that half is between 0 and 1, right? So that means this 1/2 is that type that's going to come down and go across through at 0, 1, and then continue on. Now the 4 is going to be what? What do you call the 4 in this case? That's your initial value. The number in front of an exponential equation is always considered to be the initial value. That's your y-intercept, if you will. It's going to start at 4, and it's going to decay at the rate of 1/2. So at 1, just for fun, what is 1/2 to the first power? It's 1/2. What's 1/2 times 4? 2. So at 1, it's 2. 2, so that makes sense. And let's go ahead and put 2 in there. What is 1/2 to the second